Okay, for this particular example, it's asking us to find the bending stress at position A and B within the beam, and then this red here is the beam, right? And then the positions A and B are just A and B, right? So basically, when we say A, we are talking about this whole thing here, this whole section of the beam up to here. So even if I check what's here, I check what's here, they should be the same because they are being bent in the same way, and there's a center of curvature, right? And then B is right here, right? So the first thing we do, we record the equation, right? So the bending stress equation at any point, we said generally, how is it? This, let's write this out. We have this, right? At any position, you have minus m on Rn minus r all on Re bracket Rc minus Rn, right? That is if there's no direct force applying on that particular position that I want to check, right, within the beam. But if there's a direct force, we add this. We add P, or that force, on the area, or that's the cross-sectional area to be exact, right? So here, what are we trying to find? When we look at this particular position A, the only thing that will cause a stress within this section of the beam, this A here, is the bending moment, because there's no direct force applied, right? So in that case, we clear this off and we try to find the bending stress at positions, right? So before we do that, we have to make sure we have every parameter we need. So we have the bending moment given directly. Rn, we are supposed to find that, right? R, because we are trying to find at the position A, what's the R? The R will be, the A here is the inner fiber, right? So to be this R I here, right? Yeah, which we find it to be the same as from here to here, which is this distance given here, right? That's for Re. So now let's try and then find out what each term stands for. So the R, let's see. This is the equation we're using, right? What are the things that we need? We need R, right? And R we are seeing is the same as Ri. So the R, let's go step by step. So let's see if we are trying to find the stress at E, right? We don't know that, but this is the equation for it. In order to do that, we need the moment. We have that already, which is here. We need Rn. We'll talk about that. We need R. The R is just saying the position we are trying to find the stress at, right? And that position is A, and the distance from the center of curvature to the A is what we have to be the Ri, which is the same as this 50 here. So we have R to be the same as Ri, which is 50 mm, right? We have our m already, which we have to be 4,500 Newton meter, right? Okay, and then let's see, we found R. Let's look for A. A is the cross-sectional area, right, which is 35 times 70. 35 times 70, right? And that will all be in mm, right? 35 on 70. Let's see what we get for that. 35 times 70. Okay. I do this so that we are able to follow. Okay, let's see. 35 times 70 times 70. Oh. 2450, right? 2450, that gives us mm squared, right? Mm squared. So we need RC, right? And we are saying that RC is the distance from the center of curvature to the very center of this, right? And how do we get that? What we said about the RC is that it never changes. It remains the same. You just look at the what do you call it? The cross-sectional area, right? And get to the center of the cross-section, right? Just from the center of curvature, So from here, so this the center will be about here, which is half in between, right? So that RC, what will it be? It will be this 50 here plus half of this 70. So we move from here to here, which is 50, right? And then we'll move half of the 70. We move 50 from center of curvature to here, and then we'll move half of the 70, which is 35, right? So that gives us 85. So RC to be the 50 plus half of the 70, right? And that gives us 85 mm, right? So we know our m. We found that r, which we are seeing is this. We found out a. We found out RC. The only thing left now is the Rn, right? So the Rn is actually this way. This, the Rn, which we are seeing is based on the loading as well as the coordinate, the geometry of the figure. But the RC is just based on the geometry, right? So our Rn, right, it's actually an integral, which is we have this a all on integral b actually in respect to r, so on the cross-sectional area, right? So it's actually on 1 on r, right, with respect to a. But generally it ends up with something of this sort. We have a, and then we have b, and then we have length, right? R naught, which is the outer radius, inner radius, right, of this, right? And if it happens to be a complex figure, we just sum of them, find these values and do the sum of this, of each and every part of the whole figure. Okay, same for the RC. If it ends up being a complex figure, we just do a, just a sum of it, Ri product, and then we do sum of their R's, sum of each R, like their C, right, their center, right? It's actually the area, sorry, it's area. So we get area, so we get the center radius of curvature, right? Okay, so now our aim is to find the Rn, right? So to find that, Rn will be the area which we found already, which is 2450, right? And the b here is just saying that if you look at this, the figure or the loading system, this is the center of curvature, right? So it moves and then comes to outer fiber, right? When you take the cross section of the beam, just the, what do you call it, the width of it, not the necessarily this one here, but the width up here, which one, right? Kind of like the thickness of the beam, yeah, the width. So that's the b that we're talking about. That's the 35, right? So we have 35, right? And then length of our outer, which is from center of curvature to the very out, to get that will be 50, right? From here to here, which is 50 plus the 70, right? That gives us 120, right? And then the R inner, which we know is just from here to here, which is the 50, right? So 50. Let's see what that gives us. So that's 2450, right? All on 35 times length of 120 on 50, and that gives us what are we getting? Oh, this was 50. Yeah, so that gives us 79.957. Let's do 2 decimal places, mm, right? The unit, very important. So now we have everything that we need, but then to make sure that we are moving in a particular way, we just ensure that the units are similar, right? So we have a in mm squared, rc in mm, right? Rn in mm. The only thing in m in a different unit of distance here is just the moment, right? To make our work easier, I just change only that one so that we get it in mm, right? So when we get this is what we do to get it in mm. So you have the value first, 4500, right? I want to change this to mm, so that will be times 10 to the power 3 Newton mm. And why is it so? When we introduce this mm here is actually 10 to the power minus 3. So this that's why I bring this one here to take care of this. We cancel out, it gets to back to what we started with, right? So this is what we are using for our calculation. 4500 times 10 to the power 3 Newton millimeter, right? So now that we have everything, we can find the stress at A, right? Bending stress at A minus, and then what do we have? 4500 10 to the power 3, right? Yes. This minus here is very important. This minus here, very important. And then we are assuming that everything that we are doing here, the beam is actually in tension. So if we see any negative sign, the stresses mean that to be all compression, the opposite of tension, right? So this is what we have. M, right? Now we do the Rn. We know that our Rn to be 79.9. This is 6, but we use the actual value during computation. And then our R, because we are trying to find the stress at E, right? Our R will be the radius of curvature from the center of curvature to the position of A, which is we know to be 50, right? When we look at this A, right? So from here to here is 50. So 50, right? That's it. All on R, right? Yeah, the form we have R, which is a 50 again, times the area, which we have to be 2450. And then RC. What's RC? You have our RC to be 85. Minus our RN. This minus 79.96. So let's see what we get for that, for the stress at E. To punch in this, you have this 4500. Brackets 79.9572 minus 50 50 times 2450 85 79 point this point 9572, and that gives us minus 218.22, let's say 6. And because we are using everything we did all calculations in mm, you have megapascal, right? And because this is negative here, we assume that the beam is actually in tension, right? So this will say that at the position A, the part of the beam there will be in compression, and then we can actually even look at the physics of it and actually confirm that it's actually in compression, right? So look at it here. If you're having a bending moment here, by bending it, this side here, this braid beam here, this part of it will be compressing, right? So it's very clear what's happening there. So that's why we have a compression there, negative sign, right? Negative compression. Okay. So now the next thing is to find the stress at B, right? So let's see. The work becomes much more easier if you write everything out. So we are trying to find the stress at B, combining stress at B, which we don't know. When you look at the equation, the bending stress equation is this. We have minus M, and we have Rn minus R, right? All on RE, so okay, RC minus Rn, right? Then again, the moment is the same, right? The Rn doesn't change because of the loading system, right? The the neutral radius, right? And then RC is the same based on the geometry, right? A is the area, sectional area is the same. The only thing that's changing is the R, because we are trying to check the bending stress at a different position. So at B, we have our R, right, to be the same. This is towards B, right? This is B here, and B is actually at the outer part, right? The outer fiber of the beam, the curved beam, right? So we have our R to be the same as our R outer, which we know is 50 plus the 75, right? So that gives us a 70, right? So that's 50 plus 70, so that gives us 120 mm, right? So that's the only thing we need to find our stress at B. We have the rest already. So stress at B minus, right, the moment, right, which we've changed to millimeters, 4500 10 to the power 3, 4500 times 10 to the power 3, right? Our Rn we know to be 79.96. We've approximated, but use the actual value. Okay. Minute. Okay. And then we have R here. We said that R here is what, 120, right? All on R, the same 120, right? We are looking at the formula R, right? And then our area, cross-sectional area, doesn't change. We have it to be 2450. Yeah, 2450. 2450, right? Our RC not changing, just based on the geometry. We have that to be 85, right? 85. And then we have our Rn again, not changing, because of the, it's based purely based on the loading, based on the loading system and the coordinate system, right? Which you have to be 79.96. 79.96. You can do the approximation during writing it, but just it's safe to use the actual values when calculating, right? So the only thing that we are changing here is the R, right? Which now he is 120, so 120, right? R change here as well, 120, right? Area is the same, Rn is the same, RC is the same. So what do we have? We end up getting 121.539, that was 6 megapascal. And because there's no negative here, it's trying to say that it's actually in what? Tension, right? Which in short, most of the times you write it as T, just T, right? And we can even look at the beam and say it, right? We are applying a bending moment here. There's a bending moment here, right? It's bending. So basically, this side will be in tension. The fiber here will actually be stretching, right, to be in tension, but this one here is being compressed, right? So that's the difference between the signs, and it's very important to maintain this negative sign here, this one here, when you do the computation, so you won't get it right? So the bending stress at B is tension, the bending stress at A is compression. So that's it for this example. All right.